Well, I hate to cut that off because that's such a good topic. Maybe we can revisit it in Slack and continue that discussion. All right, so the session today, right now, in the next hour, is going to be the session 3 of the Lego blocks exercise. We had session 1 on Wednesday, was talking about performance metrics. Session 2 yesterday, we had some pre-selected arrays. And we looked at the suitability of those arrays for the various science goals that we focused on. Today is presentations. The plan is going to be 5 minutes for each group, followed by a 5-minute discussion. And so that we'll do that for each group, and then we'll have a short recap at the end. And the lineup just follows the schedule that's on the public schedule. We'll go fundamental physics, then black holes and their cosmic context, jet launching and accretion, transients, and new horizons. So that's the prelude. Fundamental physics, you want to go first?
Hi, Garrett. Yeah, sure. Just give me one moment. Thank you. All right. So this is a very quickly put together talk in the few minutes that I have available to me. So first of all, I'd like to say it's a real pleasure to give this talk on behalf of the Fundamental Physics Working Group, and really enormous thanks to Carrie and to Michael as being our facilitators. They really helped connect us with this because, you know, as theorists, I think we are perhaps the most far removed from all of this. So this has been a really informative and educational exercise for us in helping shape our scientific ambitions. We're always used to thinking about things purely theoretically, and to think about things in terms of instrument requirements and which particular requirements tie in with different aspects of the science that we want to pursue has been very helpful. I think that this is really a first step. And so we looked at a few different things, and I'm going to come back to this slide. But one of the things that we looked at was 3 different options. So Carrie presented us with 3 options for different array configurations, which you can see here. Options 1, 2, and 3. So options 1 and 3 were equal cost. Option 2 was pretty much exactly twice the cost. And one of the things that we were most interested in was having a very good dynamic range, both in terms of the image and in terms of the snapshot itself. And this is because we're primarily concerned with strong gravity. So we're looking at things that are very close to the event horizon. This is where we really want to hone in on. So option 2 offered the best dynamic range, but at quite considerable cost. And in the end, option 3 seemed somewhat better. We'll show images in a second. So at the sacrifice of a little bit of baseline sensitivity and point source sensitivity, it actually offered us the best image reconstructions of M87. So if I can skip this slide, and it won't let me. And so if we have a look here, so this is comparing options 1 and 2, and perhaps many of you now are familiar with these wonderful outputs. You can see that the logarithmic contours for M87 and option 2, which is the high cost option, are a lot better. So you are resolving structure close to the horizon. This is the more expensive option. And as you can see, option 3 actually is quite comparable for M87, single snapshot. And we were quite content with that, actually. And because at the end of the day, we're interested in looking at things like the central brightness depression, which is currently resolved to about a dynamic range of 10. But if we can push that a lot further, then we can actually be very constraining on the kind of compact object we're looking at. So it's very important for us. Of course, we want a very good and a small field of view as well. We want reasonable point source sensitivity. So now if I return to the original table here, if you look at our requirements for baseline sensitivity, now this is all very much subject to discussion. We didn't go for the very low end. There's a little bit of discussion within the group about that. But since these are roughly Jansky sources, around a few Jansky up to about 10 Jansky, milliJansky is probably acceptable for us. Angular resolution. So we're theorists, we're looking at strong gravity. We like the highest possible angular resolutions possible, of course. Dynamic ranges as high as possible. And we are quite interested in long-term monitoring as well if we want to look at photon ring substructure. And so, let me move this out of the way. There are some discussions, and in brief, our major priorities at the present time are resolution and dynamic range. I've talked about these pre-selected arrays, and we actually determined that the higher priced option wasn't the best for what we were interested in. But what I should say is that we assumed smaller, so these were, I think, 4-meter dishes in the ngEHT array configuration as opposed to 6-meter ones. And this changed things quite considerably for Sag star. Sag star images really didn't look as good. And so one of the big critical assumptions so far is that we haven't really considered Sag star and the challenges that are posed by resolving that source. So not just the time variability, but also the effects of the diffractive scattering scheme, refractive scattering scheme, and so on. And so that, you know, the question as to how we balance those different challenges in resolving one source, Sag star versus M87, which is a much simpler source, they remain open and they haven't really been discussed within the group. And so there are a few questions which remain. I think there has been a lot of progress made, and I think most of all, it's really started to shape the way we approach this and think about our science. So this has been excellent. We haven't really had time to touch on polarization. So there are 2 questions about linear and circular polarization fidelity. And we haven't really had a chance to explore this. We do know that we want good linear polarization fidelity because we want to map the couplings of fields, not just electromagnetic fields, but also potentially other light fields as well, like axion fields. So the question remains as to the utility for us in the working group thus far with circular polarization, since then you have lots of Faraday effects and plasma effects coming into play. We are very interested, so I think a few people, including Shahar Hadar, talked about these opportunities to probe photon ring structure and substructure using spatiotemporal autocorrelations between photon rings. And this is, in a sense, a sort of competition between point source and baseline sensitivity. This is something I think we need to explore within the working group too. And finally, there are some potentially conflicting requirements in terms of angular resolution field. I say conflicting, that's not quite the right word. Let me take that back. There's some contrasting requirements. So we want a very narrow field of view and high angular resolution, but people who are interested, for example, in the JETS working group, they would want a wider field of view and they would want to resolve the jet at different scales as well. And so, you know, I think there needs to be a lot of discussion there, we determined, between different working groups as well. So the conclusions are that I think we want to resolve stuff on the very smallest scales. I think this is a very nice starting point. I think it's been enormously beneficial for the working group. And to wrap up, I mean, there's a lot to discuss here, but I should say thank you actually to everybody that engaged in this. It was really, really enormously beneficial and educational exercise, I think, if I may say, for everybody involved. And thank you again to the facilitators as well for doing such a splendid job. That's it. Thank you.
All right, thank you, Ziri, and all the folks who contributed and the working group this week and in the working group in general previously and going forward. So we can spend a few minutes on questions now. If anyone has it, please raise your hand in the chat. Yeah, Alexander, go ahead.
Okay, it's a fundamental question. So. But I dislike supermassive black holes because it's very uncertain. So if you assume that is really, it's a Kerr paradigm. So it's something, it's a strange question. I suggest to substitute supermassive black holes, galactic centers, because people suggested boson stars, fermion balls from dark matter and other things. Otherwise, it's not quite clear. It's in this question, we, let us say, reduce area of fundamental physics questions if we use supermassive black hole in this, let us say, key question. Yeah. Thank you.
Sure. No, thank you, Alexander, for your question. So, okay, we aren't restricted by the assumption of it being a supermassive black hole, at least in this working group, right? So, first of all, one of the reasons that we want things like very good dynamic range is because we do think that it is eminently possible, and even the Nobel Committee noted this in their award of the Nobel Prize, for a supermassive compact object. And this is very much in the front of our minds, which is why we want things like high dynamic range, because the depth of natural brightness depression is very much a function of the not just the plasma physics, but whether there is a horizon or not, what kind of compact object it is. The radius of that bright ring feature is very intimately connected to the unstable photon orbit radius in that space-time. These are all things which can be probed in this working group, and we are not in any way restricting ourselves to black holes. We have the freedom to vary the metric tensor in any way we see fit in all of the different ways we approach this. So this could be predicting photon ring structures. This could be in doing full time variable simulations of plasma around different space-times, not just black holes. So yeah, I take your point on board, but rest assured, we're keeping all these possibilities in mind.
If there aren't any other questions, I'll ask one. You talked through some of the conversations that happened about cost, and that was one of the reasons we wanted to introduce, selecting some pre-selected arrays and kind of thinking through at a high level, if this costs double but gets you better performance, is it worth it? And that's a really loaded question. It's something that requires a lot more detailed study. But I'm interested if you can expand a little bit of, how did you make the value decision of double the cost doesn't buy you enough in that example?
Yeah, no, that's a great question, Garrett, and I fully agree. It is a loaded question. So we kind of agreed at the outset, or at least the beginning of day 2, that we wanted a pretty good baseline sensitivity and point source sensitivity, but image dynamic range was really of paramount importance to us, because we think one of the key drivers in advancing this with the ngEHT science case for really starting to answer this question of, is it a black hole, or at least what is it not? We really need to push dynamic range. This is probably almost a primary consideration. Now, in terms of why we were happy with an equal lower cost option 3, compared to the double cost option 2. Well, it didn't offer much more gains in terms of dynamic range for the extra cost. It had a few more sites to the array, but it didn't give an enormous benefit in terms of baseline sensitivity. And when we did look at the reconstructed images of M87, which I think provide ideal photon ring science, it really didn't seem to make much of a difference, at least. So let me bring the slide. Excuse me, let me exit this. There we go. So these are just snapshots. But here we go, for example. There is a lovely visibility amplitude plot, which Michael just added just as very recently. I don't know if, Michael, you want to jump in and say something about that if I bring it back to that slide. Where are we?
Also, if I could jump in while you're finding the next slide. So as Ziri said, the double the cost wasn't that interesting, but that also just started the discussion of, well, wait a second, if we had that extra money, and we expanded dishes, how would that help? So, and I chose 3 arrays, but certainly there could have been a different array that doubled the cost that did actually make a difference. So that did become a little bit part of the discussion. Thanks, Ziri, go ahead.
No, thanks, Kara. I really appreciate it. Yeah, so I don't know if Michael's online to talk through this plot. This was literally added at the last moment. If he's not, that's not a problem. I'm sure we can come back to it a little bit later. But to cut a long story short, to wrap up on your question, Garrett, in the end, it just didn't seem equitable for the cost to have no real gain in terms of photon ring science. And since we are interested in, photon ring is probably one of the major pathways for us to actually start to answer these questions about, the actual fundamental parameters, or if you will, the multipolar structure of black holes, like constraining the mass and the spin and so on. That all fits within that. That's a beautiful tool to do that. And also we want to resolve, small scale structures in space and time that are orbiting around the black hole. And again, I don't think that this option 2 that we were presented with really, none of us felt really
Didn't give you enough.
Yeah. So
Great.
like I say, I appreciate that this is a very early stage in all of this, but I have to say, like, just to re-emphasize, it really has been, I think, a really beneficial exercise for everybody involved. It was really, really good to do this. So thank you.
Great. That's great to hear. And sorry, we will have to move on. Gopal, maybe you can add your question if you have it in the Slack so that we can fit all the other groups. So let's move on to black holes in their cosmic context. Jose, you want to?
Yep.
Sharing?
Second. Okay. All right. Okay. So first of all, I would like also to thank facilitator Gary Fitzpatrick and Jonathan Winthrop for all the help and all the participation from the working group. It has been really a lot of fun to play with the different arrays and try to figure out which one could actually, be the array that we need for our science requirements. So before getting into that, let me just do a quick recap and the reason why we have selected actually several science cases for a working group. And in a working group, we are interested in three main themes, which is to understand black hole growth, to study binary black holes, and to perform multi-wave studies of black holes and jets. So we did the exercise to try to find one main science case for each one of these three different themes, and from the first one we have selected perform a demography study of masses and spins of about 10 sources, for binary black holes to spatially resolve binaries, and for multi-wavelength studies to try to catch up a neutrino event with the ngEHT. Below you can see the technical requirements that we described on our talk on Monday. So having those in mind, we went to the exercise of trying to figure out what would be the array requirements to fulfill each one of these three main science cases. And as you can see here, we have identified them and discussed the different requirements that we need. Before getting into this, because we are going to see this also in the following slide, let me go to the case, the practical case that we discussed of first considering or focusing on one of these and discuss also how this may affect for the other science cases. So the science cases in which we focus was to measure these 10 supermassive black hole masses and hopefully to have a constraint on the spins of these black holes. And these are the different metrics and the number we were discussing. For us, baseline sensitivity seems to be the most important issue. We need to keep in mind that most of the sources that we are expecting to try to determine these black hole masses and spins are going to be very weak. We are always talking about Sardine and Mediterranean, but these are beasts. These are really bright sources. But the sample of sources we may be dealing with could be 20, 50 milliascale or even below that. So this could be really an important and extremely important metric for the baseline. We also realize that without actually knowing what would be the sample of sources on which we will be looking at, it will be difficult to get into a final number here. So we discussed that it would be very useful to have to try to in the next month to create a sample of possible ngEHT targets and out of that samples try to check what would be the array requirements to observe the most promising ones and to try to get at least a sample of 10 sources. Then we discussed point sensitivity, point sensitivity, and we found that for us these are 0.1 to 1 milliascale seems to be fine, but this is not something that is too relevant for us. Angular resolution, of course, is one of the main drivers for the science cases, and this is particularly extremely relevant if we want to determine this 10 supermassive black hole, we need to have this the highest angular resolution possible. And it may be that even 15, the nominal angular resolution we could get at 345 is not enough. So we were discussing, we will need to perhaps to do some hybrid imaging, combining model fit in the UV plane with imaging and so on, to try to get the angular resolution we may need. The field of view for us is not particularly important. I mean, as for the case of M87-Sage, even with current ngEHT field of view should be fine. And but it could be different for the case of binary black holes. In this case, the field of view will be determined by the separation between the two binaries. Dynamic range, the image dynamic range. Here for trying to get the black hole shadow is not that relevant, and perhaps with 100 we could be it will be able to reach our goals. But for other cases, like for the binaries and neutrinos, we think that we will need something between 100 and 1000. And we also discussed that these things that are getting larger than 1000 may be actually quite difficult. Regarding the snapshot dynamic range, in our case, this is not relevant because in principle, we don't need to do any dynamical imaging, so it's not a metric that for us plays a significant role. And regarding polarization, for two of the main science cases, I mean, for the measuring the supermassive black hole masses, it's not necessary actually to have polarization. And even probably not for binary black holes, although it may help. But for the case of multi-wavelength analysis and neutrino events and gamma ray events and so on, this could be important. And since it could be, a game changer to try to determine what is the jet composition and other aspects of the jet physics. So we think that this, in that case, it would be particularly relevant. And there are all the other metrics that we think should be also considered, which is the need for monitoring programs. And for the case of just observing 10 masses, 10 supermassive black hole masses and spins, in principle, just a single snapshot is enough. But for binary black holes and for multi-wavelength, this is a key aspect. It's really absolutely fundamental. I mean, we cannot just go with one snapshot a year. So we will need to monitor the programs. And in the case of binary system, perhaps with a cadence of a few months, but we may need to monitor for years, even for 5 or even 10 years. For the case of catching the multi-wavelength flares or catching neutrino, we will need to a higher cadence, something like days, weeks, and we may need to extend it for months. And besides this, also there is a very important need for the array, which is to have a rapid response. So we want to have an array that can quickly do a target of opportunity observation when we have an event that we would like to follow. So these are the main array requirements that we discussed, and then we were given the 3 different array configurations as they are shown here. They have a different amount of ngE antennas and different diameters from 10 to 4 meters, and of course different costs, and the cost really goes down as you decrease the size of the new ngEHT dishes as expected. Then these are the array specifications that were given to us regarding baseline sensitivity and angular resolution and so on for these 3 different arrays. And there was some discussion about what really these numbers may mean. And we arrived to the conclusion that it seems that the values reported here, and every week I have a discussion later on about this for your excellent app, it may refer to the best possible case for all the 3 different frequencies or 2 different frequencies we will be considering. So in the case of option 1, which also contains observations at the 86 GHz, we see a baseline sensitivity which is even below 2 millijansky, or really excellent. And then there is a significant jump when you go to 235, even if you have more antennas, and well, in this case, the sizes of the dishes are a bit smaller, but the bandwidth is significantly larger. So this should be, something that should help a lot in baseline sensitivity. But the values were significantly worse, and it seems that it's because 86 GHz observations were not considered in this array. Similarly, we have
one more minute or so.
Perfect. Yes, and then for the third array, we have here the values, and you can see the values we have are very similar. So the main difference is baseline sensitivity and a little bit of some changes in dynamic range. Oops. And this is the final slide, which summarizes what we were discussing before. So just very quickly here, then the array 1 seemed to be the one that offers the best combination of performance. It was probably the most expensive one. We noticed that there is not significant improvement in dynamic range with the other array, so it wouldn't really be of significance for us. As I mentioned before, we should discuss again what really mean the metrics that we were given, and also for us, we realized that the final image sensitivity may be more important actually than point source sensitivity. And there are critical assumptions that we made. I think we have discussed all this, but let me point out also to a very important thing that Neil commented, is that all these metrics may be based on the fact that we can transfer the phase array to very weak sources and still grow thermal noise. And this is something that we really need to investigate, because this may affect significantly the baseline sensitivity. So this is a very important thing. And finally, and the bigger question also is, in our case, it would be really very important to have a sample of possible targets to refine the numbers we are using. And this is all. Thank you very much. Happy to take.
Thank you, Jose, and great job walking through that for us. We've eaten into the questions a little bit. If there's one question, we can take it now. Otherwise, I'd say let's direct the questions to Slack. All right. Yes, please direct. If you have questions for Jose or anyone else from that group, please put that in the Slack. All right, let's move on. Thank you again, Jose and team. We'll go to jet launching and accretion. I'm seeing slides, but I'm not hearing anyone.
Matt, it looks like you're muted. Right? Are you the one presenting?
Yeah, I'm some technical issues. Avery, would you be able to share the screen of the presentation? Can you hear me at all?
We hear you now. Yeah.
I'm wondering if Avery could put up the presentation, because I'm having some technical.
Okay, sure. Is it the same one that you?
Yeah, the edited link that I sent you.
Okay.
Sorry about this.
Let me get it up. This guy.
That's the old one, I think.
Okay. And let me.
Should we come back to you guys?
Yeah. Why don't we come back in one?
Sorry.
Okay. No problem. We'll go to transients and then we'll jump back to you guys.
Okay, cool. Can you guys hear me okay?
Yeah, we can. Thanks.
All right. So first of all, I just want to preface this with our transient working group leaders, Rob Fender and Daryl Haggard, send their apologies that they couldn't be here for this session. So you guys are stuck with me for the next 5 minutes. All right. So the main science question that we focused on here were how are jets powered and accelerated in stellar mass compact object systems. So mainly focusing on X-ray binary systems, but we also want to explore other types of transients, TDEs, GRBs, supernova, fast blue optical transients too. And with these other types of transients, we can get at more specific questions too. For example, what physical processes could govern the different stages of gamma ray bursts, and how the local environment comes into play there too. So what observables do we need to actually answer these questions? Well, we need to be able to track jet components, measure their proper motions, starting at the beginning of these outburst events and throughout their evolution. So looking at the different science metrics of how we actually make this a doable task, when it comes to sensitivity, we're looking at something in the Milojansky range is what we're going to need. And this is based on the known X-ray binary population, and as well as typical fluxes for other transients like supernova and F-pods. Now we note that GRBs and TDEs might be too faint and too far away to actually be able to do this kind of science with, but I'll get to that a bit in the future study section. I've also highlighted kind of the really important metrics here in orange. So onto angular resolution. So when it comes to these kind of transients, what we really need is a range, we need to be probing a range of angular sizes, because we need to track these expanding jet components before they become resolved out. And that means that we require both long and short baselines. So essentially what we need to do is we need to kind of figure out the balance between probing smaller scales and extending the time over which we can track these components when it comes to angular resolution. And to put some kind of numbers in front of you, with X-ray binaries, for example, the jets are likely to have opening angles of less than 5 degrees. And this translates to expansion rates of anywhere from 0.1 to 10 milliarc seconds per day, which means that they're likely going to be resolved out between 20 minutes and 9 hours. Now, a similar kind of metric is, of course, the field of view, or the max angular scale that we can probe. And this is, when it comes to this metric, this really kind of defines our ability to track the jet components out to larger distances from the compact object. Now with X-ray binaries, we're looking at proper motions of anywhere from 1 to 100 milliarc seconds per day. So we think we should be able to be tracking these components on sort of daily timescales. And this should also allow us to connect these kind of millimeter VLBI to centimeter VLBI images with something like the VLBA, for example. And this kind of metric also ties into what the cadence of our observations should be, because that's going to depend on how long we can track the jet components. When it comes to image dynamic range, this isn't really a big factor for us. It's more the snapshot dynamic range, because these transient sources are evolving so rapidly. So again, for X-ray binaries, we're looking at speeds of 1 to 100 milliarc seconds per day. So that means that we expect them to be moving over a beam length. Let's say the beam's like 25 microarc seconds. This is going to happen in tens of seconds to minutes. That kind of gives you an idea of how long these kind of snapshots need to be. Now, the dynamic range in these snapshots is really important, because this defines our ability to actually detect the jet components. Better dynamic range means we can detect possibly paired components or multiple ejection episodes. And like you heard in James's talk the other day, this is what we really need to be constraining jet speeds and ejection times and really get at the physics. When it comes to polarization, we're really only focused on linear polarization, because circular polarization hasn't really been detected in many sources. And in the ones that it has, they're pretty not that most significant detections. When it comes to linear polarization, this is really key to probing magnetic field geometry. And we also had a bit of a discussion as to whether this could help us probe the jet composition too, but we didn't really come to a concrete solution on that. And just to kind of give you an idea of the linear polarization levels we're looking at in X-ray binary jets, at least, it's usually a few to tens of %. And lastly, the other factors is actually pretty important for this science. And this really comes down to how fast can we trigger these observations, or how fast can we slew the telescopes. All of these transient sources are going to rise and fade the fastest in the submillimeter. And also kind of tied in with this is our ability to coordinate with other facilities, whether it be ground-based or space-based. So to give you an idea of the kind of trigger responses that we're hoping for, acceptable trigger responses are anywhere from hours to days for most of these transients, and sort of the ultimate wish list would be minutes. But I do note that some of them, like the supernova and the F-bots, could have longer time scales acceptable for trigger response, more on the order of days to weeks. We also discussed some other factors, like for instance, having the ability to do absolute astrometry could also open up some more science here, where, for example, another thing James discussed the other day was the possibility of actually tracking the binary orbits in some of these extra binary systems. So given all of this, all these metrics, when we were designing our arrays, we made a few assumptions. One of them was that we're always using this partial array. So that means not all EHT sites. So for these purposes, we were using LMT, SMA, and GLT. And we chose these ones because they're the ones that sort of EHT has more control over in a way right now. We also assume the use of multi-frequency synthesis too. So the key metrics that we found to define our different arrays were really the field of view and max angular scale, snapshot dynamic range, and sensitivity. So when it comes to kind of distinguishing between the sort of the minimal viable product and the really expensive arrays, what it comes down to for transients is kind of a trade-off in the level of science we can do. Now, while metrics like the field of view and the max angular scale don't have a lot of wiggle room, we need what we need to be able to track these jet components. When it comes to, say, snapshot dynamic range, at minimum, we could be able to track a single ejected jet component. But at best, we can track multiple components, paired components, like I discussed before, which is really important at getting more physics out from these observations. And in terms of sensitivity, at minimum, we can probe a subset of this transient population. At best, we get at fainter systems. And especially in terms of X-ray binaries, we can get at different stages of jet evolution too. So to give you an idea of kind of the array parameters that we came up with, kind of the middle ground array here was 10 ngEHT antennas, 3 EHT antennas, 6 meter diameter, 12 gigahertz bandwidth, and multi-frequency capabilities. And going to what we need to do for future study. So a big thing we need to do is we need to better predict and simulate our pool of targets. So this means how many X-ray binaries can we hope to observe? Are GRBs and TDs actually realistic targets? We also want to further investigate the value of multi-frequency synthesis on our snapshot UV coverage and image quality. The brilliant ngEHT Explorer tool gave us a lot of information, but we couldn't really distinguish the role that this was actually playing on creating better images. So we need to do further investigation there. And also, perhaps the most important thing is we need to assess the feasibility and develop procedures for trigger response. There's been a lot of discussion in the Slack on this already this week. So we need to consider things like, can we rapidly get on these sources, let's say a subarray of ngEHT stations, and those could auto trigger larger antennas? Can we use multi-wavelength facilities as triggers from X-ray to optical to centimeter radio arrays? And there was also some discussion about the possibility of EVLBI, but I think the general kind of consensus on that was our data rates are just going to be too high for ngEHT. But nevertheless, we still need to kind of discuss these options as well. And yeah, that's all I've got. So thanks very much.
Great. Thank you so much, Alex and team. Real quick question. When you said multi-frequency in your middle ground, did you mean, what was that, all three? Did that include 86?
Yes, yeah. So that included all three. And that's kind of what I was getting at with one of our future questions. It wasn't clear whether, 86 and 230 could be enough, or adding the 850 micron band was going to be helpful. Was the fact that if we go up that high and we have to deal with weather and other difficulties, is that going to kind of offset the benefit that it gives us? That's something that we really need to look into.
Okay, great. Thank you. We're also a little short on time for questions, so I'll direct you to Slack to follow up with Alex and others from that group. Thank you again, Alex and team for putting this together. Can we go back to Jets?
Yeah, I'm ready if Avery's ready. Great.
All right, we can hear you. Go ahead.
Yeah, so our group is, again, the amalgam of jet launching and accretion, and there's a lot of science, key science topics to discuss. So we had a little vote, and we decided just to talk specifically about this first question here, which is whether spin energy extraction is the primary mechanism for powering AGN jets. And this was limited to essentially Sag Star and M87, the discussion. So we talked a little about what you have to do to address this question in terms of observations. And it's basically tracking these rotating substructures. And you want to compare that to what's going on very close to the event horizon. And this involves tracking features that emerge and accelerate along helical field lines. There's some discussion about whether you need absolute astrometry for this. Something that really came up frequently was the emphasis on polarization mapping. And this was to characterize the magnetic field strength, the dynamics of the magnetic fields, essentially looking at the polarization structure in the images to get this information. And because you want to get those quantities, you really need multi-frequency and simultaneous multi-frequency in order to account for Faraday rotation, get rotation measures, because you want to be able to compare the absolute electric vector position angles to the theoretical models. So that was a prominent topic of discussion. Also, using multi-frequency observations to get course shift and combination rotation measure, get magnetic field strengths from that. Hand in hand with this is that ngEHT alone won't get you the kinetic jet power measurement, and it's quite possible you'll need contemporaneous measurement of the jet kinetic power. So that's going to need other supporting observations, and potentially the black hole spin measurement as well might have to come from a combination of ngEHT and other facilities. So we can go to the next slide. So we looked at different metrics and different arrays, and up at the top there was a general agreement. I mean, there's large uncertainties here, basically because we don't quite know what the brightness temperature of this jet emission is going to be very close to the photon ring just outside of it. But again, what it boils down to in this specific case is, ngEHT has already observed M87 and Sag Star. So the question becomes, what improvements do you need for ngEHT to address this question of spin energy extraction? You can't do already, obviously, with the HT. And the big one is multi-frequency. The next is getting as good high angular resolution as you can. You can see there that the arrays, it's just a bit below the metric that we had, which was 10 microarc seconds. So we did have some discussion about whether it's possible to go to higher above 340, 600 gigahertz and above. I think general sentiment was that's very expensive. And then you run into problems of antenna design being incompatible with the lower frequencies. So it's very difficult to have both 86, an antenna optimized for both 86 and 600 at the same time. So that's an engineering challenge. So the next one there we have at the bottom left was the polarization fidelity. Certainly for a lot of the accretion modeling comparisons to theory, you need very good fidelity in both linear and circular. And the circular is typically more difficult because the signal strength is lower. The synchrotron radiation is more linearly polarized. This is based on centimeter and millimeter polarization, existing data that we have. I mentioned dynamic range, and then this has come up in the previous presentations as well today, is that observing cadence is very important. Being able to get consecutive days to make these type of movies, and then the rapid response. Certainly be able to see when there's a high energy flare and be able to go onto the target with ngEHT. So that rapid response capability. We did discuss the idea of the combination of dynamic range and rapid response might be difficult because of the fact that if you want to observe the diffuse structure, you need the short baselines, and you want those short baselines to be as sensitive as possible. So that means they need to be close to ALMA, but then ALMA is not going to give you the rapid response capability. So this is kind of an unresolved issue. How do you handle that? How do you get an array that can respond TOO and has good sensitivity on short baselines? We talked a little about the metrics as given to us. The polarization metric, you can see there it's percentage. We had some debate about whether that's percentage of total intensity peak or polarization intensity peak. And also, how does the EVPA fidelity? So if you want to measure the vector position angles to absolute accuracy or accuracy across the image, that's not sort of contained in that. And there's no real metric there for image RMS in the different Stokes Q and U. So that is folded into baseline sensitivity. So that might need some more tweaking there. And then just to wrap up, then we did talk about this availability of simultaneous multi-wavelength observations, which is crucial for this as well, for providing the triggers for the flaring observations. And then being able to close this angular scale gap. So be able to track those field lines further out, be able to do that with maybe ground at 86 gigahertz and even down to 43 if you can connect those disparate scales. So that's about the summary we have, and that I can give in 5 minutes.
Great job. Yeah, thank you, Matt and team. We do have maybe 2 minutes here for questions. If anyone has them, please raise your hand in the chat. And if not, we can direct questions over to Slack.
Garrett, I actually have a question. I'm just having trouble finding a hand.
Okay, go ahead.
What simulations, I think, do we need to prioritize over the next few months to get clarity on the science side of this question? Maybe that's a question for the group as a whole.
I'll just chime in that from what I've observed as a little bit of an outsider in the simulation world, more simulations of the partial arrays that get at these questions about this balance of response time to target of opportunity and also short enough baselines to achieve the kind of sensitivities we need. I don't know that we've really exhausted that the amount of combinations of arrays and really tried to define different scenarios along those lines. Marshall, go ahead.
Actually, I think my question was basically the same. I was just going to ask, would it be useful to have 4 ALMA antennas as they put as a possibility on their wish list? Because we discussed that a fair amount. As a subarray, just to have a short, small subarray. Would that be useful? And I guess but I think you kind of dealt with that in the previous question. So I'm sorry. I just, we did discuss that, and it seems like it might be useful in some cases a lot.
Do you mean new dishes, or do you mean kind of subnetting ALMA to?
In the one of the ALMA presentations, they talked about how they have this, what we called a wish list. I don't know, I forget what they called it. But basically, one of the things on the wish list was the ability to have up to 4 antennas treated as totally independent from the network. So you could just use these 4 antennas to set up a small VLBI array, for example. And so we were talking about, well, for some cases that would be very useful. If we, even 1 might be useful for the things we were talking about, but it seems like if you don't want just a small subarray, 4 might be very useful, particularly if all the other antennas were more or less the same size. So, you know, you'd have more or less the same sensitivity from the ALMA antennas as from any others. And so, no, we're not putting new antennas there, but using the ones that are already there.
Great. Yes, thank you. This is something you should look at. We are short on time. I see TK and Polly both have questions. I just direct you to Slack for those so that we can fit in the last group, if you don't mind. All right, so last group is New Horizons.
All right, thanks, Garrett. So unfortunately, Andre isn't able to come here, so I'm presenting on the behalf of the group. And let me find my window. So we had a very interesting discussion here in New Horizons. As you might remember from Andre's Monday discussion, we are focusing a lot on science cases that relied on some kind of phase referencing. There were many we pursued. But one of them that doesn't overlap a lot with what's going on in other groups is the idea of measuring velocity fields across the sky, and then perhaps teasing out via secular parallax something that would help us inform the nearby Hubble constant, say maybe up to something like on the tens of megaparsecs range. So what do we get from the high frequencies here versus doing this at lower frequencies where it's much easier? Well, the idea is that you know, besides getting much higher resolution to get much better precision of in astrometry, we also have potentially much simpler sources to deal with. We might see all the way down to the photon ring, or at least a much more stable core than a lot of the dynamics that are happening at lower frequencies. So it turns out that our secular parallax signal can be actually pretty large. You know, so for it's pretty reasonable within 80 megaparsecs or so, we might get parallaxes within that might be on the order of 10 microarc seconds or so per year. And for this particular science of trying to tease out the Hubble constant, we thought we might need several targets to look at. And for each target, also, you know, thinking about how many calibrators we would need nearby within, say, 10 or so degrees, we would ideally like several calibrators, reference sources, to deal with any systematics from the calibrator targets themselves. You know, the parallax measurement benefits from a long time baseline, and if we could observe many times per year, that would help even more. So we would want to revisit these sources over a long period of time. So maybe a couple times to several times per year over a decade would be ideal. One of the major challenges for this group was that we just didn't really know what targets to look at. And I think this is a big problem in our business in general. We don't have a very good handle on the structure and availability of calibrator targets at very high frequencies. So we used as a nominal nearby source M87 as an example. This is one where we know we can detect a photon ring and we know its distance. We didn't really know what calibrators were nearby, so that's something we'll have to study or propose to survey in the meantime. But we're also considering other samples, for example, the ones that Neil presented, or things that we know about, like Sene, which is closer. Maybe we can't exactly see the photon ring, but we can still see quite deep into the core of the source. So when we talked about requirements, the fact that we didn't exactly know what the properties of our calibrators were makes it very hard to pin down many of these, but we did our best using guesses. So in baseline sensitivity, we didn't want to exclude too much. We decided 100 millijanskis was an absolute minimum, just with the idea that, you know, if we had much worse sensitivity, we wouldn't even be able to see much of M87, but we probably really want a better sensitivity than that. And then in terms of angular resolution, well, we do want the resolution that we would be provided from the high frequencies and the long baselines that ngEHT has in mind. The field of view and dynamic ranges aren't actually that important. We don't need a lot of UV coverage to centroid these. We were hoping for relatively simple sources, right? We're not trying to do wide field imaging of dim extended flux. And similarly, we don't really need polarization fidelity, except for the fact that we don't want it to mess up our source structure measurements from contamination. So we left this at 10%, but it's worth future study, but there's no reason to go to very high polarization fidelity requirements here at the moment. Just in terms of what arrays we were considering, I think this is on the next slide. These all were tri-band telescopes and receiving systems simultaneous, and this is required for our phase referencing concept. And then as explained to us, all of these concepts here have a similar total cost, and they differ pretty much in balancing number of antennas versus antenna size. And it was pretty unanimous in the group that we really favored larger, more sensitive antennas versus more smaller antennas. And that's because we suspect that the calibrators we'll have available to us are quite dim, especially if we're restricted to a small region around our nominal target. So we want to get as much sensitivity on a single baseline as possible. So that was pushing us toward this, 4 new stations with 10-meter diameter dishes, giving us the best sensitivity. But we don't even know at the moment if that's sufficient. But that's where this ranking lies. And I think that's the end of this presentation.
Okay, great. Thank you, Lindy and team. We could probably take one question if anyone has any right now for New Horizons. Okay, we'll move on to the recap. And if you have any questions, again, we'll put those in Slack. We'll keep the discussion going there. Again, thank you for team. It was a really, really good summary. So for recap, I just wanted to share this one slide and kind of talk a little bit about next steps. One kind of some thoughts that I had as designing this exercise and going through the various discussions and now seeing the presentations. The minimum viable arrays that we came up with are pretty diverse. There's a big range of different designs that may be viable, and that I think reflects a lot of the diversity of different science cases that we're considering. So we've got some work ahead to resolve some of that. Another point, most of the groups I think really only had a chance to focus on one question. There are many more questions that need to be considered and needed a deeper study also. So we will be expanding on this effort in the coming weeks and months, again, with the idea of trying to get us closer to narrowing in on technical requirements. This is going to take some time to work through, but I think this whole exercise is a really good step to try to define specific areas that we need to follow up. Okay, so what's next? The science working groups are focused on writing these key science goals, these documents, so that we have a clear understanding of those goals and what their implications are. We have a systems engineering team now, and you've met most of them. We'll be working with the science working groups. We will be building a clear traceability from question to design. And maybe more specifically, we're going to be following up with the leads of the working groups. We're going to start attending some of the working group meetings and try to keep the engineering considerations front of mind as we start getting into trade-offs. And then milestone wise, we've got a system requirements review that's intended to start finalizing some of these requirements. It's right now, it's in the spring, and we can talk a little bit more of kind of implications of those and the specific plans as we get closer to the requirements review. All right, with that, thank you everyone for all of your participation and engagement. Thank you to the working group leads for your time filling out the survey, putting in the values and kind of helping to lead those discussions. And thank you to the facilitators for jumping in, many of whom are fairly new to the team, and really appreciate the willingness to jump in. That concludes. We'll take a break now, and I believe the next session is in 15 minutes.
And next up is the Shattering Stars film by Peter. And we'll start at noon, right? Or in 15 minutes, that is.
Yep, sounds good.